So this whole table right here is something you'll have to have memorized. And the thing is, we've already talked about the path integrals, right? We've already done a path integral over a scalar field, where we have a path gamma with a parameter t, and you take the derivative of, you take gamma prime of t, and then you take the norm, and then you put that in your integrand along with your scalar field. And then that's just regular multiplication, because that's a scalar times a scalar. When we did a path integral over a vector field, we took gamma prime of t and we just left it. We didn't take the norm, but we just left it as a 3-entry vector. So that way we did the dot product with the vector field, which was also a vector of 3 entries, dot product of vector of 3 entries, for that kind of integral. So the new stuff today is this stuff, right? The new stuff today is saying, hey, let's look at a parametric surface, which is some surface defined with parameters u and v. And if I want to take a surface integral over a scalar field, then it's going to be a double integral where I take the integral over my domain. So these bounds of integration are going to be the bounds of u and the bounds of v. And inside my integrand, I've got my scalar field, obviously, just regular multiplied with the norm of, this time it's the cross product between the partial derivatives of your parametric surface, Ru cross Rv. And then for a surface integral over a vector field, you'll see in your homework your textbook calls these flux integrals whenever you do a surface integral over a vector field. And you get that from physics, right? If you do a surface integral over, let's say, a magnetic field, so a magnetic field would be a vector field, then you would call that magnetic flux. You'd be asking, what's the magnetic flux over this surface? You could also say the same thing for electric flux if you've got charged particles moving through an electric field. Or I'm not a physicist, so I don't exactly know what I'm talking about. But the word flux comes from physics, and if you take these kinds of surface integrals over vector fields in physics, they often use the word flux to describe what you get.
Yeah, I remember it, back in high school, we're doing have this kind of wire, a circular wire, and then it has a oriented surface, and then there was a magnetic field that is perpendicular to the surface.
Yeah.
So we would try and find the value of the magnetic field, doing some integration, but not double integration.
Mm-hmm.
Not double integration, but just one integral.
Yeah. Yeah, exactly. So, has everybody had a chance to write this down in your notes?
I took a picture.
Or take a picture?
I'm being efficient.
Yeah, because you have to write this down if you're going to memorize it. You have to memorize it if you want to, pass your exam next week. So this is the form that these integrals look like if you're talking about a parametric surface, right, with parameters u and v. And I like putting these side by side with the path integral because this helps me remember things. If you can remember what the path integral formula looks like, then the surface integral formula looks really similar, right? I think, anyways. If you have a surface that's defined explicitly and not parametrically, right? So instead of having a parametric surface, what if you just say z is a function of x and y? That's still a surface in 3D space, but it's not defined parametrically. You could still kind of work this into a parametric surface, and you could say, well, let me give a surface with parameters u and v, where the x-coordinate of my surface is just u, the y-coordinate is just v, and then my z-coordinate is just the same function, but I could say it's a function of u and v instead of x and y. Okay. So you can always convert an explicitly defined surface into a surface that is defined as a parametric surface, or a system of parametric equations here. What that does here to our formulas, if you wanted to simplify these formulas, is, let's look at the scalar field first, I guess. Let's talk about, if I want to take a double integral over a surface of some scalar field. This would be the scalar field times the norm. Remember, the norm is just where you take the square root of all the entries squared. And this was supposed to be the norm of this vector, RU cross RV. Let me just write it as the norm, and then I'll do the square root later. dt. Did I copy that right? Oh, yeah. Yeah, okay. Good point. This is a surface, not a path. And so I actually have two parameters. And my two parameters I'm calling u and v. Yeah. Okay. So let's figure out what is RU cross RV first. And get that out of the way. So that cross product is going to, man, I need that thing to get out of there. Okay, that cross product is the determinant of the 3x3 matrix looking thing. The second row is going to be the partial of this parametric surface with respect to u. Oops, partial of x with respect to u, the partial of y with respect to u, the partial of z with respect to u, and then the last row is going to be the partial of this surface with respect to v. Okay, so if I take that determinant, then I get this cross product. Okay, but I just said that my parametric surface has this form where x is equal to u, y is equal to v, and then z is some function of u and v. Don't know what that is, but I'm just saying broadly this is what it would look like to have an explicitly defined surface that you convert into a parametric surface. Okay, then that means over here, the partial of x with respect to u, if I just say x is equal to u, then that partial is just 1. And then the partial of y with respect to u, well, y is equal to v, so that partial is 0. The partial of z with respect to u, we don't know that one. But this partial of x with respect to v is 0. This partial of y with respect to v is just 1. And then, again, I don't know what the partial of z with respect to v is. Okay, so now we take this determinant. And so this determinant is going to be I times 0 minus 1 times the partial of z with respect to u. And then negative j times 1 times partial of z with respect to v. And then k times 1 minus 0. Okay, so that is the cross product between these if you are starting off with an explicitly defined surface, right? Okay, then the next thing I would do is I would take the norm, and the norm is just what you get if you square all of the entries and then you add them together. And so let me replace this whole norm thing with just squaring all of the entries of that vector, adding them together, and then taking the square root. So that would be 1 squared plus the partial of z with respect to u squared plus the partial of z with respect to v squared. Okay, and so this is what you would get as your formula if you have an explicitly defined surface, and we can even go one step farther. And just remember that x was equal to u, right? And then y was equal to v. And so I can go back through here, and let's just replace all the u's with x's and all the y's with v's. Ta-da. Okay, so if you are given z as a function of x and y, again, that's what we call an explicitly defined surface, then you could just use this formula instead. It's the double integral over x and y of your scalar field times the square root of 1 plus partial z with respect to x squared plus partial z with respect to y squared dx dy. But I do this whole exercise because I want to point out that an explicitly defined surface is just a special case of a parametric surface. So these equations sort of work broadly for any surface, whereas the formula we just found only works for explicitly defined surfaces. So it's up to you which one you want to work with. We could do the same thing for flux integrals, for surface integrals over a vector field. We could do the same thing and get a formula that just works for explicitly defined surfaces as well. We might do that if we have time. So let's do this example. In this example, lowercase f is a scalar field, just because it's not a vector, it's only got one thing here, so it's clearly a scalar field. And then my surface is an explicitly defined surface, right? So I've got z as a function of x and y. That surface is kind of a paraboloid shape. It is a paraboloid shape because z is going up with the square of x and the square of y, so it makes kind of a bowl. And notice that I'm only considering the surface where z is between 1 and 9, because I don't want z to be 0, because then I don't know what my scalar field is. My scalar field would be undefined at z equals 0. So that way I can avoid that singularity. And if I want to take this surface integral over a scalar field, I can write this as the double integral over, I'm going to call this R, and this is going to be a region in the xy plane, because again, this is an explicitly defined surface. So I can take the integral over, we'll call it like dA, but it could be like dx dy, just as an example. And then what goes on the inside for my integrand is my scalar field times what we just found a second ago. It'd be 1 plus the partial of z with respect to x squared plus the partial of z with respect to y squared. So partial of z with respect to x is 2x, and if I square it, then that's 4x squared. And obviously it's the same thing for y. So this double integral becomes the double integral over some region in the plane of x y over z times the square root of 1 plus 4 times x squared plus y squared dx dy. Now, just like with path integrals, I don't remember if you I don't remember if, well, I don't know if you remember doing this with path integrals. I remember it. Whenever we had the scalar field, and the scalar field is a function of x, y, and z, we could go back to the definition of our path to get x, y, and z as a function of t, and then we plug the t's into our integral, right? Well, in this case, I'm taking the integral with respect to x and y, and so I only want variables x and y inside my integrand. And I've got this z, so I'm going to replace the z with the definition of z according to my surface. So I'm going to replace that z with x squared plus y squared. Okay. And now I will ask the audience, what do you guys think that I should do next if I want to make it easy to solve this integral here? Did you say polar coordinates? Yeah. I was making sure I heard you right, but yeah. In polar coordinates, r squared is equal to x squared plus y squared, and I've got x squared plus y squared popping up all over the place. That is a clear indication that polar would be a nice, neat way to go. And in polar coordinates, x is r cosine theta, and y is r sine theta, and then x squared plus y squared is r squared, and then this becomes the square root of 1 plus 4r squared. And then what does my, what are these little, what's at the end here? What am I missing?
R, D, R, D, theta.
Yeah, r dr d theta. I can't just write dr d theta, but I have to write r dr d theta. Cool. Few things I notice is the r squared cancels, top and bottom. And so that's really just cosine theta sine theta.
And I think we can use it inside of that.
Yeah, definitely. And I could use a u sub, because that's going to end up nicely with the little r we have left over. Right now, I'm going to start being careful about the bounds of my double integral. So what is the region that I'm integrating over in the xy plane? A circle with a hole in it. Exactly. Very good. So my surface is the paraboloid z equals x squared plus y squared, but I'm only okay with z values that are between 1 and 9. And I know if x is 3 and y is 0, that gives me a z value of 9. And I know if y is 3 and x is 0, that gives me a z value of 9. And if x is negative 3 and y is 0, that gives me a z value of 9. And if y is negative 3 and x is 0, that gives me a z value of 9. And so this circle in the plane represents the outside bound of my paraboloid, because that's where it reaches z equals 9 above the plane. Okay. And then you said with a hole in it. Where does the hole come from? Yeah, the circle of radius 1. And that's because anything inside that circle of radius 1 is going to give me a z value of less than 1. And I have to respect this inequality here. So it gives me a circle with a hole in it. You might see this word in your textbook. This is also called an annulus. But that's going to be my region, is that annulus. And now that I'm converting from rectangular to polar coordinates, and polar coordinates, what would be the lower bound on r? 1. And the upper bound? 3. And then the lower bound on theta?
0.
And then upper bound? 2 pi. Perfect. So now, Gabriel, what's my u sub? U equals
1 plus 4x or 4x squared.
Yeah.
Yeah.
So then du is equal to that r here. So with the u sub, we have integral 0 to 2 pi of integral from, what's my lower bound?
Oh, no, it's
5
5,
And upper bound,
plus 7.
37.
Yeah, you're right, my bad.
And then what I get is cosine theta sine theta u to the 1/2 du d theta.
And we have to put 818, right? On the outside.
Yeah, oh yeah. Good reminder. So then I've got 1/8 times integral 0 to 2 pi cosine theta sine theta. And then this is, yeah, u to the 3/2, which means I pick up a little 2/3 out here. And then I have to plug in 5 and 37. And then that's going to be d theta. Ugh. Okay. Not really nice numbers. And so that's 1/12. This is just a constant. This is a really ugly constant. It's 37 to the power 1.5 minus 5 to the power 1.5. Okay, so forget about that. And then we've got integral 0 to 2 pi of cosine theta sine theta d theta. And how do I get rid of that last integral?
It is 1/2 sine 2
What cosine theta times sine theta is?
1/2 sine 2 theta.
Oh, really? Okay. So what I was thinking is,
I
yeah,
I was thinking Yusuf.
if I just say
Is that what you
sine
said?
theta, then this is pretty easy.
Is that what you said?
But you know what you're talking about is, I'm sure it would work too if you know that trig identity. I just don't know that trig identity. So now this is just the integral from 0 to, what is sine of 2 pi? 0. Integral from 0 to 0 of w dw.
Wow.
How about this?
Okay.
Oh.
0.
No, it would be. No, yeah, you're right. Oh, that's
Okay, so
So I remember these from like Calc 1. There was like needed to memorize, and I just completely forgot about it. Yeah, sine theta times cosine theta
Oh.
sine 2 theta over 2.
so this is 0, right? I mean, an integral from 0 to 0 is 0. And so no matter what you're multiplying by, this is still 0.
That's
Let's talk about why this might be 0, right? So this is, again, we're talking about a surface integral over a scalar field. And my surface is radially symmetric, right? So it's like the same in all directions. If you're looking away from the z-axis in all directions, it's the same thing. My scalar field is going to be positive in the first quadrant and the fourth quadrant, but it'll be negative in the second quadrant. No, I said that wrong, right? It's going to be positive in the first and the third quadrant, and it'll be negative in the second and the fourth quadrant. But other than that, it's actually the same values, right? They're just positive or negative. So like the first quadrant and the second quadrant are going to cancel each other out. And then the third quadrant and the fourth quadrant, those will cancel each other out. And so it actually kind of makes sense if you think really carefully about the symmetries here. It makes sense that this surface integral should be a 0. It would be a more interesting question if we only thought about like maybe the first quadrant. And if we were only thinking about the first quadrant, like, you know, from here to here, what would be my bounds on theta? We would say theta starts at 0 and goes to pi over 2. Okay, so just for the heck of curiosity, we could say different problem, now changing gears, different problem. What if we only think about the surface that lies in the first quadrant? And in that case, this wouldn't be 2 pi, this would be pi over 2. And then what is sine of pi over 2?
It's 1.
It would be 1. And so the antiderivative is 1/2 w squared, so this would be 1/2. And so the value of that flux integral, if we change the problem, not what we started with, but just a different problem where we only consider quadrant 1, it would be 1 over 24 times this really ugly constant. Okay, so there is positive flux if we only think about the surface that lies in the first quadrant. But if you think about the first and the second quadrant, then it would cancel each other out because they would be the same but opposite, right? Going for the first and the second quadrants only would be 0 to pi, and sine of pi is also 0, so then, yeah. Any questions about this one? Lingering questions about it?
So if it would have asked us for the answer for like the whole structure, we would put 0.
Yeah. Yeah, the correct answer to this problem, as I typed it out, was 0. And if you're really an expert, maybe on your exam, you can look closely at my problems and think about the symmetry. And if you think about it hard enough, maybe you realize that the answer should be 0, and you can just write a 0 and move on without having to do all the math.
Flat 0.
Is it allowed to do that?
Yeah, I mean, if it's correct, yeah.
Okay.
If it's correct, and I know you know, if you didn't cheat, I'm assuming you're not like pulling out your cell phone and using
Okay.
Wolfram Alpha, as long as you're not doing that.
But yeah,
Um,
the problem is like higher dimensions, like visualizing how to check for symmetry.
Yeah.
Yeah.
I gave you a question on one of these exams. It says, what is the divergence of the curl of a vector field?
0.
Yeah, and so some people did all the math and found that the answer was 0. But also, you could have looked on this little handout I gave you the other day. And the last thing I put on the handout is that if you've got continuous second partial derivatives, then the divergence of the curl is 0.
Yeah.
So you could have just written a big 0 on that page, and that would have been
I
fine.
remembered that, but I was scared.
You were scared.
Like, calculating it, like 0 was weird.
Okay. So that's one example. Let's try to get through a couple more. This one, we've got another scalar field. This time, I've got a parametric surface. So my surface is defined with parameters u and v. This time, well, I avoided the problem from the previous example, didn't I? Because if you really think about this, 2 cosine u, 2 sine u, v. What that's telling you is we're talking about a surface that is a cylinder, and the radius of the cylinder is 2, and the height of the cylinder is 1, right? The only place where the v appears is in my z coordinate. So I'm saying let the z coordinate go from 0 to 1. And then in the x and y coordinates, we're talking about a cylinder with radius 2, except whenever I say that, I'm only letting my parameter u go between 0 and pi halves. That means I'm only talking about the quarter of the cylinder that's standing up in the first quadrant. So this avoids the same issue that we had in the previous example.
Like a portion of a k.
Yeah.
And then 0 to 1 will be.
So this is not going to be 0. If it were the full cylinder, I think it would be 0 again, but in this case, no. Well, I take it back. I don't think it would be because of the plus z. So never mind. I don't think the full cylinder would actually be 0. But anyways, here we go. Surface integral over a scalar field. The way we do this is we say we're going to take a double integral. This double integral is going to be over my parameters u and v. And what goes in the integrand is the scalar field itself times the norm of the cross product between the partial derivatives of my parametric surface,
DUDV.
du dv. And so the lower bound on u is 0 to 2 pi halves, and then the bounds on v is 0, 1. Okay. If this is r, then ru is the partial derivative with respect to u, and that's going to be -2 sine of u to cosine u, 0. And then the partial with respect to v is going to be 0, 0, 1. So whenever I take this cross product, taking the cross product is finding the determinant of this 3x3 matrix looking thing. Okay. And for the first entry in my resulting cross product vector, that's going to be 2 cosine u times 1. For the second entry, or the j entry, that's going to be -2 sine u times 1. So that'll be +2 sine u. And then for the third entry, or the k entry, that's going to be 0. Then what we have to do to take the norm of this vector is we've got to square the entries and then add them all together. And so I will copy everything down again down here. Integral 0 to 1 of integral 0 to pi half of f, and f is x, y plus z. And then this norm is going to be the square root of 2 cosine u squared, so 2 squared times cosine squared, plus 2 sine u, all squared, so 2 squared times sine squared u, and then du dv. And you're right, cosine squared plus sine squared is just 1, and so I've got the square root of 2 squared, which is just called 2, and that does away with my whole radical over there. And then I have to plug in for x, y, and z. I have to make those in terms of u and v, because that's what I'm integrating. I'm integrating with respect to u and v. And so x as a function of u and v is given by my parametric surface. That's 2 cosine u. And then y as a function of u and v is 2 sine u. And then z is just v. So just to remind, this whole section with the radical, that's just equal to 2. But then this whole section is where it got interesting, and we had to expand it out in terms of u and v. Any questions about that step? All right. We've got another situation where we got cosine times a sine, and we could do that. Maybe we could do that u sub again.
I like all it is just take a sine, and I mean you can take out the 2 on the, it would just be cosine times sine. You just double up.
Yeah.
Or do you want to try with, since we have a 2 in there, we can do like without I suggested is sine 2u over 2. And then we just have sine 2u.
I need to go ahead and just break this up into two integrals because it's like giving me a headache looking at the plus v part.
It is.
And so,
It is like-
so let me make it into two integrals, and then I can think more clearly about this. So here's the first one, which is just 4. So I'll make that an 8. Cosine u sine u du dv. And then now we can write plus 2 times the double integral 0 to 1, 0 to pi over 2 of v du dv. We can do that because antiderivative additivity and so on. Okay, assuming I haven't made any mistakes so far, then what are we going to do over here? I would prefer to do the u sub, but we're already using u, so let's call it a double u sub. And the double u sub is going to be sine u. So dw is cosine u du. And that integral becomes 8 times integral 0 to 1 of integral. What's my lower bound now? Sine of 0 is 0. And then my upper bound, sine of 2 pi, or sorry, sine of pi over 2, 1. Okay, my new integrand is w, and then I have dw dv. Okay, plus over here, we are taking the antiderivative with respect to u, and that's not very hard. So this is going to be uv, where I evaluate the u part at pi over 2 and 0. So that's clearly just going to add a pi over 2 constant, which is just going to make that 2 into a pi. And I just get v dv. Okay, back over here. Antiderivative of w is going to be 1/2. And this would be w squared, but we're going to plug in a 1, and we're going to plug in a 0. So that's just 1, right? 1 squared is 1. And then if you make that a v and plug in 1, then this is just 4. And if you make that v squared over 2 and plug in a 1, then that is just pi over 2. Okay, so there's your answer. 4 plus pi over 2. All right, you guys. Any questions about that one? Got a neat little parametric surface integral. I've only got 5 minutes left, but I want to show you an example with vector field, right? It'd be sad if we never did a surface integral of a vector field, or as your book calls it, a flux integral.
Flux capacitor.
Yeah.
I don't know.
So, double integral over a surface of f, which is a vector field. And this is a surface that is defined explicitly. I say it's defined explicitly because we have z equals some function of x and y. A is just a constant, we can pretend A is 3 or 5 or whatever. But like I said, we can always take one of these explicitly defined surfaces and pretend that it's an parametrically defined surface, right? And so if this were a parametrically defined surface, we could say that, x is u and y is v, and that would make z the square root of a squared minus u squared minus v squared, right? I'm just converting explicitly to parametrically defined. Because I haven't memorized the formula for the explicitly defined surface, but I have memorized the formula for the vector field integral over a surface, and this was a double integral over my parameters u and v of my vector field, which is x, y, negative 2z, dot product with the vector that is a cross product between RU and RV. So if this is my R, right, then that means RU is the partial with respect to U. That's going to be 1, 0. And then the partial derivative of this with respect to U is going to be negative 2u divided by 2 square root of a squared minus u squared minus v squared. Is that right? Fact check me. Because it's the 1/2 power. So if you take the derivative, you bring down the 1/2, right? So I got the 2 in the denominator. And then the 1/2 power becomes the negative 1/2 power, which puts the whole square root in the denominator. And then chain rule says times the derivative of the inside, which would be negative 2u in the numerator. Okay, so that's r sub u. And then the partial with respect to v would be the vector 0, 1, and then the same thing but with v. So negative 2v over 2 square root a squared minus u squared minus v squared. Obviously the 2's in the numerator and denominator will cancel, and then I want to take the cross product of these two vectors. So let's take the cross product, which is the determinant of this 3 by 3 matrix looking thing, and then it's 1, 0, negative u over square root a squared minus u squared minus v squared, and then 0, 1, negative v over square root a squared minus u squared minus v squared. So this is going to be a 3-entry vector, 3-dimensional vector here. And then the first component is going to be 0 minus 1 times negative u over blah, blah, blah. So the first component is going to be u over square root a squared minus u squared minus v squared. The second component, the j component, is going to be negative 1 times negative v over all that junk minus 0. So v over square root of all the junk. And then the k component is going to be 1 minus 0. Okay, so that is that cross product vector that shows up in the integrand. And I'm going to take the dot product between x, y, negative 2z and that vector we just found. Then, once we have that dot product, which is just element-wise or entry-wise multiplication, and then you add them up, we're going to have to replace the x and the y and the z with u and v and the square root of a squared minus u squared minus v squared. And then we just have to do the little integral over u and v. And actually the bounds of this integral are not going to be super fun. I say the bounds aren't going to be really fun because if you think about this surface, z equals the square root of this stuff. This is actually the top half of a sphere, right? So square both sides and you get z squared equals a squared minus x squared minus y squared. Add x squared and y squared to both sides, and you would get x squared plus y squared plus z squared equals a squared. So this is the top half of a sphere with radius a. So the half of the sphere that lies above the xy plane. So whenever you set up the bounds of this double integral, and u is really the same thing as x, and v is the same thing as y, you're going to have to think about parametrizing over the circle with radius a in the xy plane. And then you're probably going to want to switch to polar coordinates at some point. Like once you get done wading through the crap, you would say, okay, let me switch to polar coordinates to finally solve the integral. That's going to be the easy way to do this solution.